Okay, so today's video is going to be about relativity. Relativity. Okay. In relativity, we'll be talking about change in time as how it affects the frame of reference. Reference. Ref. Okay, so frame of reference. Reference. Okay, so what I mean by frame of reference is, let's suppose if I'm standing on this 2D or this 1D road. It's a road, okay, and I'm standing on this road, and I see two players shooting a ball. I will see that they both. Let's suppose not two players. They're one player. There's one player, and he shoots a ball. So the ball will go up, and it will be again caught by a person. He jumps and catches the ball. Okay, caught. So this is happening. This is happening when velocity is zero, or is, I won't say zero, is less, because zero, I will tell you why I didn't say zero. Even if we see the same thing when you are in a car or a truck moving somewhere, because of the speed, still a truck or a car can go a maximum how much, right? Let's suppose the maximum we're talking about a supercar, a car. This is a truck, but a car. No, it's a car. So let's suppose going with 180 kilometer per hour. Still, there will be no change in the uh, no change in frame. Same as stationary, because this effect, this speed is nothing in front of speed of light. Whenever you're trying to get to near the speed of light, whenever you're trying to get near the speed of light, then the effect starts happening when v approaching a is approaching is less than, let's say closer to vc, then there will be effect. This effect, what I mean by this effect is that right now this object is moving like 0.8 the speed of light. What he will see is that for him and the person who is standing here, they will observe the same thing, same event happening at different coordinates for both. Keeping in mind that VA is less than closer to VC. Okay, pardon, I'm sick. So uh, what I mean by coordinates is, let's suppose it's coordinates. I'm talking about x, y, z, and time. These four coordinates: z, y, sorry, x and y. And here's time as well. Okay, so coordinates. But for our simplicity, we'll only talk about x and only the x coordinates, the length, and the time. For simplicity, simplicity. So here, our main motto was to show that time, change in time, not time, change in time, will be huge when when change in time is nothing but time final minus time initial, right? So time final when we have more speed. More speed means the speed we are moving at speed close to speed of light. So that speed time minus this speed time, the difference will be a lot. So that's the reason. Same thing. Okay, will be huge when velocity approaching is a lot. Okay, so this is the reason time is not constant. The main concept of relativity to show that time is not how you think it is. It's different. It is not constant. Different for each observer, relative to each other observer. So whenever we're talking about something closer to speed of light, relativity will be there. Even in some theory cases, we do take the word relativity. So um, by the way, these are the coordinates x, y, z, the coordinates we mostly use for the geometry, and t is the fourth coordinate which is also being affected. Let me show how t and x, they are related to each other. That you can have scenarios in which x and t both will increase, or one will increase and one will not increase, and one will vice versa. So we can see that using graphs of space-time. Now that we have graphs of space-time, there's a reason I said space-time, because these two are taken as one entity. Distortion in space is distortion in time. Something happened to space, something happened to time, and so on. So let me show you the graph. Let's suppose this is space-time, or let me suppose it's x, this is t. So here we'll not draw any increasing or decreasing or like weird curves. We'll only go for constant lines. So we see here that as there's increase in time, sorry, as there's increase in time, there's increase in x, sorry, the interval. Change in axis at equal interval. And what is this? At equal interval with equal interval of time. But same thing I can write again, another graph I'll make. I have two green and black, so I'm a weird man. Idiot. Not man, boy, I'm only 17. How can I be a man? Okay, so here this wait, sorry, this line over here indicates that the, wait, this color I think not visible, the body is moving through time but not x, because x position change in length is in our hand. We can change length and decrease and increase, but time is not stoppable, is not controlled. It's the entity which cannot be controlled. It will go on, it will go on and on and on. You cannot stop it. But then there's the thing that you can stop the watch on the time on the watch, but that's not the physical, like that's the time of your watch stopping. That's a funny thing, right? Yeah. So then, what? How much did we do? Wow, 11 hours, 11 minutes, not that much. Okay, so then let's talk about uh, let's talk about um, do you think this is possible, moving through length but not time? No, right? Because as we said, time cannot be controlled, length can be controlled, but time cannot be zero forever. But it can be decreased. We can have this time that increase in length is more, but time is slower. As we said, speed at which that object is moving is more. So yeah. Uh, um, let's talk about Lorentz. Let's get to the mathematics of relativity. Lorentz transformation. Formation. So Lorentz transformation says that final time, improper time, is nothing but gamma of time minus VTC. Okay, and change in x is nothing but gamma of t minus, not t, original x minus Vx over c. Okay, so am I right here? Yeah, I'm right. Yeah, this way. Correct. Okay, so here let's play. Let's do experiments with using this. Let's suppose these are 2 points. Point A, point B. Distance is 10 billion years. 10 billion? Not billion, let's suppose 10 light years. Let's get easier, not difficult for the sake of the video. So, and the object which is moving from this point to this point is moving at 0.8 the speed of light, which is in gamma nothing but 5 by 3 as shown by this equation. I'm shocked I remember this, even though it has been 2 to 3 months since I did this. What was that? Okay, so this is known as Lorentz, not gamma factor. Just let's simply go with gamma factor. Okay, so what else? What else? What else? What else? We need to calculate this, right? So this entity over here shows the time which is being spent by this person. So it will be 5 by 3. That's original time. Let's suppose the one who is observing from here, for him the time will be, let's suppose 10 seconds for that event to happen. For him, I'm just assuming theory, anything can happen in theory. For this guy, only 10 seconds were taken for this person or this vehicle to go from to travel light years in 10 seconds. This is the speed. This is time. Oh, wait, not time. This is x. 10 and 3 times 10 to the power 8. I have my no, I don't have my calculator. Shah. Let's suppose, but the value will be value less than original time as velocity of the object is more. So less time. Okay, so wait, I just thought of something. Wait, I forgot. What was that? But wait. Let me give me a second. Give me a second. I was thinking about. What was it? I just had a thought in my mind. Wait. Let's get with the mind. Thought in the mind. It was. So. Yeah. We'll not go with any calculation in this video. Okay, let's suppose these are 2 points. And in these 2 points, from A to B, a person goes towards B and returns back. Okay, so he does a double journey. So whatever his journey is, d times 2. Okay, so I will make a graph for person A and person B. Let me just draw first. So the scenario we are talking about here is that the person who is going out and then returning, for him, he sends signal to the person at A, and the person at A is also sending signals. So here we will see that at this point, signals at this signal take more time to travel. So for, and over here I'll just circle the main part, this over here, less time. And you know what's the funny thing here? The moment he's okay, let's suppose he has a telescope, and through that telescope he can see that person on Earth, the point at point A, the person at A. He will see that over here there will be not that much effect, that he is going out into space sending signal and he is seeing through this telescope. He will not see any difference. But the moment we reach the end of the journey, he will see that person turning from certain age to the other age, the final age, within like minutes and hours. Those years, let's suppose these huge years are only hours for him. Who? The one with velocity approaching, not greater, approaching VC, velocity of light, and yeah, that's it. Thank